Bernoulli's equation is big. It has a lot of variables in there, and that makes it seem like you're going to solve for a lot of different quantities, so that this would be a very, very versatile type of equation. In reality, you're going to use this to solve for a handful of different kinds of problems. So this is an example of Bernoulli's principle. Okay, for this first one, I want to start with looking at Bernoulli's equation in the context of an artery. So maybe I've got the left side of my artery, but in some particular region I have a buildup which reduces the effective area considerably. So over here, I'm going to say I have a diameter. I know radius is the value that is the most helpful to get, but almost all the time when you do problems like this, they give you numbers in diameters. And we're going to say this is 50% blocked. So over here, this thing, 50% of the diameter is blocked. So this thing's going to have a diameter of 2 millimeters. We're going to have blood flow over here at 0.4 meters per second. And we're going to say there's a pressure of 13 kilopascals. I would like to find the speed of blood flow here and the pressure. And we know that blood has a density of 1060 kilograms per cubic meter. So this comes through. We're going to need some areas, and we're going to need to find this speed, and then we can do pressure. So I will write Bernoulli's equation up at the top. Alright, what we do know is in this case we are horizontal. So this term and this term will cancel each other, they'll be equal. So first we're going to find the speed here. And we're going to do that by looking at flow rate. Now we have, in the beginning, Q initial is area 1 times V1. Q at 2 is area 2 times V2. And flow rate has to be the same for both. Area. I can take the diameter, turn it into a radius, and then pi r squared this thing. Or I can look and say, if my area is pi r squared, radius is half the diameter, so this is pi d over 2 squared, or pi over 4 times diameter squared. So pi over 4 d1 squared v1 equals pi over 4 d2 squared v2. And this will work like this every time. The pi over 4s are going to cancel, which means when we're trying to find the area, if we know the diameters or the radii, we can just do d1 squared and d2 squared because the pi over 4 part's going to cancel every single time. I'm looking for v2. v2 is going to be d1 squared v1 over d2 squared. 4 millimeters squared, 0.4 meters per second over 2 millimeters squared. My diameter is being cut in half, so my speed is going to go up by a factor of 4. That's what I'm seeing here too. 4 over 2 would be 2, and then I'm squaring it, so 4. So I'm going to get 1.6 meters per second. And now I want to find that pressure. Pressure 1 plus half rho V1 squared equals pressure 2, which I'm looking for, plus half rho V2 squared, and I have all these numbers now. So my pressure 2 this works out to be 11,728 pascals, which if we had 13 kilopascals to start with, we are going down. I mean, we could probably say 11.7 kilopascals. So that's how that worked for a horizontal pipe, which was really an artery. Let's do a different one. Maybe we have a water tower. And it feeds down to something else. But one spot that it feeds is just a spigot on the end. We're going to say here is the water in the water tower. And the water starts out 30 meters above the ground. Because this is 30 meters, it doesn't matter too much if this goes to the top or the bottom. This is not going to be a huge difference compared to the 30. Water has a density of 1,000 kilograms per cubic meter, and this thing is open to the atmosphere, which means we know that the pressure here is going to be 101 kilopascals. Also, it's not like they pressurize water towers. This pressure is 101 kilopascals. The reason it's 101 kilopascals here is when we open this, it's just air pressure sticking this direction. At the top, this water is pretty much stationary. We would like to find the speed here at the bottom. So we'll get out Bernoulli again. We have to pick a spot to be height equals 0. I like here. So that's 0. The pressure is the same at the top as it is at the bottom. We don't have anything pressurizing this. It's not like a closed issue. And at the top we have a speed of 0. So this thing reduces a lot. Rho G H1 equals half rho V1 squared. This looks a lot like a conservation of energy problem, doesn't it? Rho and rho cancel. I'm so sorry, I made a terrible mistake. V2 equals 2G H1 with a square root. And that works out to be 24.5. What if we close the spigot and now we want to find the pressure down at the bottom because we're not open to the air anymore? Then we would say P1 plus rho G H1. So now we're looking at this. When the spigot's closed, I mean this one's still 0. This height's still 0. When the spigot's closed, there's no water motion. So we can solve for P2. This just looks a lot like depth pressure though, doesn't it? So we're going to get our 101 times 10 to the third pascals from pressure 1 plus density times gravity times height, 10,000, 300,000 plus 101,000 looks like 401,000. So we can do a bunch of different problems with this, but they all come down to kind of the same exact equation. For the most part, when we do one of these, we will either have, in this case, we had no change in speed. In this case, we had no change in pressure. And in this case, we had no change in height.